Now it's a pleasure for me to introduce the next speaker, Shaun. Probably everyone knows him as the founder of ROS-I Industrial. He's with Southwest Research Institute, and he will present one result of one focus technical project. Shaun, it's your you have the mic.
Okay. Can you hear me okay?
Yes, I can hear you.
Okay. Thank you very much for that kind introduction. So what I'm going to do is take about 10 minutes and describe to you a ROS industrial project called Descartes that we've been working on. Just give you some background on it and let you know where we are and where you can find the source code, because that's what this is really all about. So first I'll start off with what the application need is that we see in industrial applications. It's really about path planning. And it's different than your traditional path planning that you do in ROS with a package like Move It. In Move It, it's very focused on pick and place and kind of free space path planning. In the industrial world, we have those problems, as you can see with the Amazon picking challenge, but we also have a lot of problems where we know generally the path the robot has to take because it's doing some process. But that path is somewhat fuzzy. We call them semi-constrained trajectories. And the definition of that is when your trajectory has fewer degrees of freedom than your robot. So there's some redundancy built into your system. Good examples are grinding and painting, welding. In those particular applications, the orientation of the robot tool and the process it's performing has some wiggle room in it and tolerance associated with it. So it's not purely a 6 degree of freedom pose that you want, but it might be 5 or 4.5. Other examples like deburring and 3D printing, where you basically have an axisymmetric tool with which you can rotate around and still perform the process. So that's a 5 degree of freedom problem. And of course you have redundant robots where even if you have a 6 degree of freedom pose, you have extra joints which you can utilize to position the robot in different poses. Next. So the current solution to this problem, if we were using off-the-shelf tools, and there are tools for this, is pretty much an arbitrary assignment of 6 degree of freedom poses and redundant axes. So even though you may have a 5 DOF requirement, in order to get a robot to perform it, you have to specify all 6. And these really give you limited guarantees on your trajectory timing. For a process like robotic machining, you might want a certain feed rate, and if you pick the wrong pose, the robot may not actually be able to achieve that feed rate. It also results in reduced workspaces. So if you have to maintain a certain orientation, it can result in a kind of shrinkage of the true workspace of the robot. And these processes, this arbitrary selection of 6 DOF poses, really relies on human intuition about the robot kinematics themselves, which is very, very difficult. And when that human intuition fails, you end up with collisions in the workspace. You end up with robots approaching singularities and running into joint limits for these really complex Cartesian paths that we're trying to solve. Next. So we started the Descartes project to address these problems. In short, what Descartes does is it's a planning library for semi-constrained trajectories. At a high level, the requirements that we had for this project were to first generate common sense plans. And this is kind of ambiguous, but what it really means is we want to generate plans with the Descartes planner that look like plans people would have generated themselves. A lot of you may be familiar with kind of the random sampling and the kind of random path plans that come out of that. And while that's required for kind of pick and place applications, we felt we could get better plans given the constrained trajectories we have to deal with. We also had a requirement that we be able to find easy solutions fast, but also be able to find hard solutions given enough time. So our methods and our planners had to scale to the complexity of the problem. We also had to handle hybrid trajectories. So trajectories that include joint waypoints, Cartesian waypoints, and even specialized waypoints that may be specific to a process like painting or grinding or welding. And then finally, we wanted to be able to do fast replanning or cached planning so that if minor modifications were made to the plan, we could very quickly replan without having to start from scratch. Thanks. So we're about midway through this software project or the development on this project, but we already have one application example under our belts. We call it robotic routing, similar to robotic machining, but we're cutting parts out of thin sheet metal using a router. As you can see in the images there's a reasonably complex path that represents the outline of a part we'd like to route. And on the right, we're using a very large, very stout, sturdy KUKA robot to perform this robot routing task. The trajectory can really come from any kind of source. It could be scanned, it could be coming from CAD, but that's the input to the Descartes planners, is a semi-constrained trajectory in space. Next. So given this first application that we tried, we've been able to achieve 800 5-degree of freedom waypoints planning in 30 seconds, which is good for this application. It's an offline planning application, so there was no real-time requirement. And it's a reasonably complex path, which kind of moves in full 3D space with large orientation changes. So we're proud of that performance. We think we can do better, but we're proud of it as it stands. The current path planners have to minimize something or optimize something. They currently just work on minimizing joint motion while adhering to all the trajectory constraints. Replanning, we've been able to achieve as near instantaneous. So when changes are made to the trajectory, they happen almost instantly. And we do have support for hybrid kinematic path planning at this point. We're working on getting full trajectory or timing built into our planners in the last half of the project. And if I can, I'd like to show a YouTube video. So if you look at that video, what you'll see is our path planner working on that path that I showed in the previous slide, and also showing kind of the human interaction going on that allows a person working an offline planner to adjust the path as they need. Again, giving us that instantaneous replanning. So where we are, we're doing all of our development out in public, so everybody can see our pull requests, all the reviews that are going on, every commit that we're doing, which is both good and embarrassing sometimes, but we like you all to come see what we're doing. We expect a ROS industrial release of Descartes in the second quarter of 2015. In the video, you'll see a really nice GUI that sits on top of Descartes. We'd like to release that open source, and we're working towards it, but we don't have a date for that release. And finally, I'd like to acknowledge all the people that helped on this project. The developer team includes Dan Solomon, who was formerly with Southwest Research, myself, Jorge Nicho, and Purser Sturgeon, all with Southwest Research. And also, this project was supported by NIST funding and ROS Industrial Consortium funding as well, and we appreciate their support.